All right, let's start looking at triglycerides. So it's basically fat and oil. Okay. So what you need to be able to do, 5 points. You need to be able to draw the structural formula of an edible oil or fat, given the structural formulae of the carboxylic acids from which it is derived. Identify the alcohol and acids from which a triglyceride is derived, given its structural formula. Identify the most likely source of triglycerides given its state at 25 degrees Celsius. So solid fat or oil. Describe and explain the use of a solution of bromine or iodine to determine the degree of unsaturation of a compound. Draw the structural formula of the reaction product. I'm thinking of doing a titration prac again so that you can remember how the titration is done, and also applying it to finding degree of unsaturation. Finally, explain the role of pressure, temperature, and a catalyst in the hydrogenation of a liquid triglycerides. Okay. Hydrogenation of that. We'll look at that. Okay. Condensation. Edible oil and fat, they are all triglycerides. And triglycerides are esters formed by condensation reaction from propane 1,2,3-triol, commonly known as glycerol. Now, what's the shape? I have the lecture note. I gave you the lecture note yesterday. Yeah, okay. All right, propane 1,2,3-triol. What does it look like? So hopefully you're thinking of the propane, the 3 carbons attached to each other. It's propane. So there's no double bond between. First, second, and third one, there should be hydroxyl groups attached. That's 1, 2, 3 propane triol, or propane 1, 2, 3 triol, either way. Now, in this subchapter, you often see this flipped around, about 90 degrees rotated around. Now, as the previous line saying, triglycerides that can be derived from condensation reaction between this and carboxylic acid. Yeah. So if you remember what you learned in esters chapter, if you have carboxylic acid and alcohol, you can make ester. Yeah. This 1, 2, 3 propane triol has got 3 alcohol components here, functional group. So if you had 3 different carboxylic acid, they'll make 3 different ester as a link. Okay. So you need various fatty acid. Now I believe if you look at page 284 of essentials, please. So you can find things like stearic acid. Stearic acid, have you heard of that? Did I use that when we did flame color prep with you guys in chapter 1? Anyway, stearic acid is one of the fatty acids. As the name suggests, it burns quite well. It burns almost like candle. So what I do nowadays to demonstrate what I call flame color prep, I ask students to melt stearic acid, make solution of it, and it solidifies and becomes with some ethanol in there as well. It becomes like solid fuel basically. And if you had some metal powders on it, metal salt on it, it will have color candle pretty much. Okay. Stearic acid has got how many? It's octadecanoic. So 16 and 1, 2 on each side, so 18 carbon, octadecanoic. And if you have looked at what's in olive oil type of thing before, you would be able to find oleic acid, linoleic acid. What's the biggest difference between, say, stearic acid and oleic or linoleic acid? What do you think the biggest differences are, apart from numbers or carbon? Yeah, size is definitely different, yes. Between, say, stearic and oleic.
Double bond.
There we go, good. So some have got double bonds, some has got only single bonds. So that will come in very handy for you to know. And on the next page there, 285, you can also find an example of triglyceride. You see that there's 3 ester links. And ester links can be derived from, on the next page, carboxylic acid, this fatty acid connected to propane 1,2,3 triol. Okay. All right. Right, now, if you have got triglycerides, they can be hydrolyzed to produce propane 1,2,3 triol, so this alcohol, and various carboxylic acids which were there originally. All right, let's draw that. So if you have that's one ester group there, and you're going to draw a few more. So that's our starting triglycerides. And if you add water to it, or in this case, you need 3 water molecules to hydrate the 3 ester bonds. Now you'll be able to make CH2, CH. It's actually CH3. No, that's right. CH2 is fine. CH2OH. That's propane 1, 2, 3 triol. And what carboxylic acid do you get? Well, whatever that was there. So instead of oxygen only, you have now OH, R, HO, CO, double bond, and R dash, HO, CO, dash. And if I highlight, oh, the red one was in my pocket yesterday. Where did the H2O go? OH group, H group, H, OH. So that's a hydrolysis of triglyceride. Adding water. Alright. Now, one quite important thing for you to think about is the state of triglycerides. Are we all good? Okay. If you look at the fat that's stored in land animals, they all solid. They're all solid at room temperature. But if you look at plants like olive oil, peanut oil, linseed oil, or whatever, they are all liquid at room temperature. Also, fish oil, something that people know it as healthy oil, the omega-3 and all that, that helps your brain function and all that. I mean, fish, they're swimming in water, and their oil in their body don't, become solid. They can keep swimming, right? So, what's the difference? That comes down to what sort of bonding carbons have in the fatty acid component of it. Okay. So, this generally contains saturated carbon chains. Sorry, when I say these, saturated carbon chains only appear in solid fat, solid triglycerides. Okay? The carbon chains only contain single bond, and they make straight chains. What that means is that they can pack close to each other, and when molecules are close to each other, what happens? They form solid. Okay, and if they can't pack nicely, because all the fats are not much bigger, the distance from one molecule to another is much larger as well. So dispersion force also becomes a bit less. Therefore, the ones with only single carbon chain, they make solid triglycerides. Hence, something that has more double bonds, they tend to be much bigger and more distance between each molecule, then they make liquid triglycerides. Okay with that? Okay. So single bonds ones only, they can become like butter. Butter though, something that is spreadable. I guess they are dissolved in some sort of plant oil. If it's spreadable, even if it's much cooler at much cooler temperature than room temperature, I suspect that it's dissolved in some oil, or it's modified a bit to have 1 or 2 double bonds like so, but it's still spreadable. It's not purely like solid like lard or animal fat that you can just cut off from steak. Yeah. Liquid triglycerides, so they the opposite of that really. They can't pack close enough to each other, so weakens the strength of dispersion force. Therefore, liquid is their state at room temperature. Olive oil. So I was looking at this before as well. Oleic acid, apparently 55 to 83% of those fatty acid that's connected to as part of olive oil is the oleic acid. So majority, I would say. And some are linoleic, some are palmitic acid, stearic acid, no double bond at all. But there are a lot of fatty acids which have got more than one double bond. Yeah, or one or more double bonds. So appear as oil, liquid. Now, degree of unsaturation is something that you can work out, or quite important when it comes to think of, I guess, health benefit of each type of oil, or how well they would stay as liquid in our body as well. Because, well, we know the like dissolves like rule, yeah? Non-polar substances like fat stored in our body can be actively dissolved away if you had something healthy, something non-polar, yeah, such as fish oil or oil that doesn't become solid in our body. Yeah. So some margarines and stuff says actively reducing fat or cholesterol level. What that means is that they become liquid in our body, and because it's non-polar, they can attach to fat content in our bloodstream or in our body and remove it in the end. So you can actually lose weight or lose fat from your body if you had some oil that can stay liquid. So unsaturated triglyceride can undergo sorry, I'll start again. So that's why it's good to know how unsaturated triglycerides are, and for you to do it, we use bromine and iodine solution. All right. Bromine is, if I'm not mistaken, brown orangey color, and iodine is, I think, browny purpley sort of color when it's in solution form. I think we'll be using bromine, red, brown, orangey-ish solution. Okay. When it gets incorporated into the triglycerides by saturating the double bonds, where double bonds are, they become clear. So you will see the color change, and as soon as the oil molecules are all saturated, you will start seeing the color again. So that's why you can do titration. All right. So here is the reaction. So for example, if you had this oil, and I'm just gonna make up this. And if you add bromine solution, which has got Br2, now I might make it 2 of them somewhere. How many molecules of bromine you would need? The reaction that would occur is C double bond with addition of Br2. That makes it C. Br. So one of the double bonds open up and grab one atom of bromine each. Yeah? So that will make CC to Br. So how many moles of Br2 would you need to saturate these double bonds? 2. As many as the double bonds are. Yeah? Because there are 2 sites where that can be fulfilled. So you've got oxygen. And with Br here attached. So 2 molecules are consumed by this oil, and now this is, I guess, saturated. And as soon as you start adding more than what's necessary, you will start seeing the color change. As you wouldn't see the color change anymore. You will start seeing the brown color liquid that you're adding to the solution or whatever you're using. Okay? So this is how you can measure the amount of double bonds within whatever the sample of oil that you're dealing with. It would be interesting to see. It would be interesting to see the difference between, say, extra virgin oil and normal olive oil. I know the extra virgin olive oil would be more flagrant, but I'm not sure if that's related to, the number of or degree of unsaturation. Or they could be the same. I don't know. They could be just more concentrated. We don't know until I do it. All right, last slide. Last slide with information. Now, we just used the example of unsaturated triglyceride, which is oil. You can also saturate it with hydrogen. We just use bromine, same reaction, but instead of using Br2, you could use H2. What would that mean? What would that mean? So in this case, for you to find unsaturation, the degree of unsaturation, you added Br2, and then by letting the color of bromine disappear, you could figure out the unsaturation degree. Yeah. If you though add H2, what that means? What's that mean?
Was this all we need 300 degrees nickel catalyst?
Yeah. Good. Someone remembered. Yes, we'll talk about the condition. If you add H2 there though, what's going to happen to the double bonds? What does it become?
Explode.
It wouldn't explode. Single bond only. That's correct. So you are saturating it. Okay. If you start with unsaturated fat such as olive oil, and add hydrogen, what's going to happen should be only single bond appearing. Because all the other carbons have got hydrogens anyway. So unsaturated fat can be converted into saturated fat. I keep saying fat, triglycerides. All right. When would that be useful? What's the spreadable things that you have for your toast? Butter, okay. That's already animal fat.
Peanut butter, margarine.
You can have peanut butter. Margarine, yeah. Do you know what margarines are made out of?
Not the same stuff.
Not the same stuff as butter. So it requires the requires chemical process for you to have olive oil spreadable thing, margarine, or canola spread that you can buy. So those margarines that you can buy, or the latest favorite that I have is avocado oil spreadable margarine thingy. I forgot the name of it. But you can buy it too. So that's using avocado oil, obviously. Now you start with plant oil. What they do is they add hydrogen to it. By saturating all the double bonds, make all of them into single bonds, they get margarine, which is solid-ish at room temperature. I guess they change the amount of unsaturation, so you can make it still spreadable at fairly low temperature, like fridge cold temperature. But yeah. So yeah, unsaturated part will become more saturated, and it involves H2. Well, we already said that. Conditions, that's something you must memorize. You require high temperature, high pressure, and nickel as catalyst. And without them, reaction rate will be too slow. And high temperature, if I'm not mistaken, it's 300 degrees or something.
That's right. Last year.
All right, and make sure you can relate this back to what we talked about in using a controlling reaction chapter. So you can explain why this increased reaction rate in terms of collision theory, yeah, heat, pressure, and catalyst. So this is for making margarine. And that's it for the triglycerides.